Okay, thank you so much. And thank you for confirming that. I want to welcome everyone to my lecture today. Today, I'm actually going to walk you through another exciting topic in statistics. And I first want to appreciate, those who actually touched by, those who actually asked about my condition. I think I'm good now. Okay. Uh, I'm I'm fine now. So thank you so much. Okay. Today, I'm actually, like I said, I'm gonna be walking you through another exciting topic, and the topic of today is a model selection. Okay, model selection. Okay, now let's get started. The goal of today, okay, we're actually going to learn how we can investigate how the predators are associated with the response. Okay, let me just say that is one of the goal of regression. Okay, of course, you study how predators are associated with the response. An example of such is when you use the rate my professor data set, where we're trying to study how uh, how the professor's quality score is actually associated, okay, with the clarity score. So you actually study relationship between the two. And of course, one of the other goals of regression is to assess the effect of one variable on the other one. An example of that, you may want to study which genes are causing the cancer, or you study how the production size effect affect production time. Okay. Then another goal of regression is prediction. We're going to have a prediction of future values of a response variable given predictors. An example of that is when you are trying to predict the professor's quality score based on their clarity score. So I'm going to say these are the three main goals of regression. Okay, so I want us to have a kind of a review. You remember the last time we met, I walk you through, ways of comparing regression models. I remember I walk you through how you can compare any form of regression model with intercept model. With that, I think we made use of AF tests. And I also walk you through one you can compare any form of regression model with another regression model, and none of that is intercept. Okay, and we also want to have a review on that. And that is exactly what I'm trying to say here. Comparing two models, you are comparing the simple model with a complicated model. The simple model has a fewer numbers of predictors compared to complicated model. And you know what? The simple model is also nested in a complicated model. I think I gave you an example the other time. And of course, before you can actually consider using the nested test or the or nested F test or the partial F test, you got to make sure that the simple model is nested in the complicated model. Now, I think I've already we walked you through that the other time, but you know what? The model selections depend on the answer of, does the complicated model fit the data significantly better than the simple model? Okay, so in statistical analysis, where we may have different kinds of competing models, and we are actually looking for the one, we want to figure out the one that will actually capture, that will adequately describe our data set. And that's why at times we to choose between the simple one and a complicated one. Why do we need to choose between the simple one and the complicated one? Why can't we just choose the complicated one? Because the complicated one may not do the job until we actually carry out, statistical tests. Okay, it's just like when you have a simple model and you just consider that, you don't, because of simplicity and consider a simple model, and you don't because a complicated model has a lot of, predators in it, and you now think it's going to be better than simple model. I think decision to choose any actually depends on empirical evidence. Okay, so that's exactly what I'm trying to say here. We got to make sure we conduct, standard statistical tests, to be able to figure out which of the model is fantastic. So like I said, you actually want to compare between a simple model and a complicated model. If the complicated model actually fit the data well, then we basically are going to go for it. So if we go for complicated model, then it means we don't believe that the simple model will do the job. Okay, there is something that is new today. Okay, I want to say the partial F test and the like, they also do the job of model selection. But what is new today is when we are selecting model, we actually have criteria that we use in selecting model. And I'm going to say there are some criteria in statistics that consider model fitness, and we also have one that consider both model fitness and model complexity. Okay, but let me tell you this. We normally want a model that will fit the data well, and at the same time, probably the model has to be relatively simple. Okay, and I'm going to tell you now, when we're talking about the model fitness, okay, we have two criteria, that measures model fitness and that we use in statistical analysis to validate our model. We have what we call the RSS or the R squared. You remember the other time I told you the meaning of RSS, that is residual sum of square. The residual sum of square is actually the unexplained variation. Because if I really want to tell how poor or how good is my model, okay, I need to look at the residual sum of squared. And I can also look at the R squared. Okay, the R squared, of course, R squared is what we call the multiple determination, which actually measures how much percentage variation in the response the predator variable can actually explain. Okay, I just wanted to take note of that. So as far as model fitness is concerned, there are two criteria, that are available, which we call the residual sum of squared and squared. And let me tell you here now, dash ROS means the more the foot the sample data, better is basically going to be smaller. Okay, it's going to be smaller. The smaller RSS, okay, means the model foot the sample data well. Okay, don't forget the RSS is the residual sum squared and is the one that we call the unexplained variation. And in statistical analysis, we basically want to minimize the residual sum of square. We want to minimize unexplained variation. And that is the reason why the smaller one we actually point in the direction that the model actually fit the sample data better. Okay, then what about R squared? We need a larger R squared. Okay, a larger R squared actually means the model fits the sample data better. Okay, don't forget that I said R squared actually measures, how much percentage variation in the response variable the model can actually explain. Okay, don't forget earlier before now, I think I actually walk you through how the response variable can actually be partitioned, okay, into explain and unexplained variation. And of course, we have a way to measure out of the 100% percentage variation in the response, how much of that, uh, the predictor variable actually explain. Okay, so like I said, the smaller RSS and the larger R squared is what actually means that the model fit the sample data better. Okay, so before I continue, is there anyone who need a clarification? Is there anyone? Okay, so I need everyone to confirm again if you are still hearing me clearly. Okay, thank you so much. Thank you for confirming that. Okay, so let me now tell you this. You know, we actually, I said something now. The RSS or R squared measures the model fitness. But let me tell you this, what if in a situation where we have a good numbers of regressors in a model? When you have so many regressors in a model, when you have so many predators in a model, of course, the regression model will actually become complex, okay? And when the regression model, actually become complex, you know what I want to show you now. Okay, how does the model fitness react to that? How does the model fitness that we talk about now, the RSS or the R squared, so how did they actually respond to increasing the numbers of regressors in a simple linear regression? Okay, now I'm going to show you now. Take a look at this now. Okay, this is simple linear regression model where you actually have one predator, right? You have one predator and you have two regressors. And of course, looking at this now, by the time we compute the RSS, the residual sum of squared, which are actually called the unexplained variation, it was 0.403. And when I actually fit an intercept model, take a look at this guy now. Okay, this is an intercept model. Okay, the intercept model here, take a look at the RSS is 4.499. This is the RSS here is higher than this. And of course, this is a bad fit. Okay, this model here is a bad fit. Don't forget, when we talk about intercept model, we're trying to say we fit a model without predator. Okay, we actually fit a model without predator. Take a look at that. Okay, so when we now try to move all the way to 5 regressors, look at this now. I got 5 regressors. Some of you may want to wonder what are my regressors in this model. Okay, my regressor is 1, x, s squared, x to the power 3, and x to the power 4. I'm going to say that again. We got 5 regressors right here now. Okay, the regressor is, when I say regressors, I actually mean the coefficient of the regression parameter. Okay, I'm going to say that again. regressors in a regression model actually means the coefficient of regression parameter. Okay, now when you take a look at it, what is a the coefficient of 10.9 is 1. Okay, the coefficient of x of 17.2 here. Okay, you actually, so you have 1x squared, x is to the power 3, x is to the power 4. That's why you get k equal to 5. But oh my God, take a look at this now. RSS equal to 0. Instead of us to be celebrating now, what I'm going to shock you now, I'm going to say we don't want the situation where RSS will be equal to 0, because we are in a stochastic world. We live in a probability space. We do not expect the unexplained to be equal to 0. There's always going to be a value for unexplained situation where you have your unexplained variation to be equal to 0, and that is what we call overfitness. I'm going to say that again. This is overfitness now. Overfitness is not good. Overfitness, we don't want that in statistics. Okay, so right now when the RSS equal to 0, okay, then it means that model actually overfits. Okay, and what is the takeaway now? There's something I actually wanted to say. When the k is increasing, when the numbers of regressor is increasing, you're actually going to see that the RSS is going to be going down. I'm going to say that again. When the numbers of regressors is going up, the RSS is basically going to be going down. Okay, when k equal to 1 here, okay, you have RSS to be 4.99. When k equal to 2, you have RSS to be 0.403. And when k equal to 5, you can see the RSS actually equal to 0. What I said, we don't want that. We don't want the situation where the RSS is going to be equal to 0. Okay, because if the RSS equal to 0, what we're trying to say is that we have a perfect model, and we can never have a perfect model. I told you the other time, even though we're trying to capture reality with our model, we don't expect our model to give us an exact reality. Okay, now I think you've already seen that now. Okay, now you've actually seen the
Can we
okay,
ask
okay,
question?
okay, go ahead.
Can we use K to determine whether that is very simple model or is like relative simple model?
Yeah, the moment K increases, the large values of K actually talking about
Yeah,
model
I mean, can we use
complexity.
K to determine whether that is the fitness of the model?
Oh, you mean can we use K to determine the fitness of a model? Is that what you mean?
Yeah,
Okay, that's a very good question. We don't use K to determine fitness of a model. The K is only going to tell you the numbers of regressors or the numbers of predictor, or maybe is actually going down. The only thing what the K is going to show, the K is only going to show simplicity or complexity. So K is going to show simplicity when the model has a smaller numbers of regressors, and it's basically going to show complexity when you have a larger, when the numbers of regressors is huge. So K does not really tell us, whether how good is a model. Okay, what K actually tell us, it measures model complexity. Does that make sense to you now?
yeah,
Okay. Now, now we've seen the behavior of RSS when you decide to increase the numbers of regressor in your model. But right now, we also want to see the behavior of R squared. Okay, I told you we got two criteria. Okay, we got two criteria when it comes to model fitness. Okay, when it comes to model fitness, we got material, two criteria. And of course, we've actually investigated the behavior of, a residual sum of squared. But right now, we also want to look at the behavior of R squared, when the numbers of regressors go up. Now, I wanted to take a look at it. And the example we want to use today is actually using the years of experience of professional workers to predict their salary. Now, when we started, we fitted a simple linear regression model, and of course, we got the RSS to be 4789.046, and of course, the R squared is 0.6754. But when you take a look at this scatter plot, you're basically going to see that there's a curve, right? You can see a curve, right? And a curve actually means, fitting linear regression will be out of place, okay? But fitting linear regression will not be appropriate, okay? Now, you now move to increase the numbers of regressor now, okay, to, initially you add two regressors, which is 1 and x, but right now, you now move to, you add additional regressor. Now we have 1x and s squared are the regressors now. So here k equal to 2, okay, and here k equal to 3. And as you can see now, the R squared go up. Take a look at that. The R squared actually goes up from 0.6754 to 0.9247. Now, if you want to decide to increase the numbers of regressor again, to see whether there's going to be a kind of significant increase in the R squared, take a look at this guy now. We decided to extend the quadratic model. Okay, we decided to go from 3 regressors now, okay, to 4 regressors. This is a situation where the number of regressors is actually equal to 4, but look at the R square now. The R square moved from 0.9247 to 0.9257, and there's something I want you to take note. The movement from, a model with 2 regressor to 3 regressor, if you take a look at the increase here, that is very, very huge compared to the, the movement from, the increase here when you go from, 3 regressors, to 4 regressors. Take a look at that. Okay, so when you continue to increase the numbers of regressor, you're basically going to see that R squared will continue to go up. But I'm going to tell you now, the RSS is going to go down, the R squared is going to go up. But let me tell you this. Even if what you are actually adding, if the regressor you are adding does not make sense, the R square is still going to go up. I'm going to say that again. Even if the regressor you are adding, even if the independent variable in the case of multiple linear regression, even if the independent variable you are actually adding, even if it is not relevant to the response, the R squared is still going to go up and the RSS is still going to go down. I'm going to say that again. If you increase the number of regressor in a model, and even if that regressor does not make sense, the R square is going to go up and the RSS is going to go down. Therefore, you cannot trust them. You cannot trust RSS and your R squared, in a situation of model complexity. I'm going to say that again. In a situation where you got a good numbers of regressors in the model, where you have a, model complexity, R squared and RSS, they cannot be trusted. They cannot be trusted even though what you are adding doesn't make sense, the R squared is going to go up, the RSS is actually going to go down. Okay, and that is the reason why we need a new Brown criteria that can actually be used to measure both model fitness and model complexity together. So what I'm trying to tell you now, okay, is just to tell you, that you cannot trust your R squared, you cannot trust your residual sum squared in a situation of model complexity. That is exactly what I mean. Then what can we trust then? And I'm actually gonna walk you through that. Okay, now I think I asked a question here. How did RSS change when we had more polynomial regressors? Of course, you can see the way it changes. Of course, it's actually the RSS is basically going to be going down. Okay, and how did the R squared change when we had more polynomial regressors? Of course, the R squared is basically going to be going up. And that's another thing I want you to know. If you look at the data set that we are actually considering here, we are still talking about one predator. The predator here is a years of experience, and the salary is the response. Okay, when you look at the first one here, is talking about the linear relationship between the salary and the years of experience. But when you take a look at here, we are actually in addition to the linear effect of the years of experience, we are also incorporating the quadratic effect. But when you take a look at this guy here, in addition to the linear effect of the experience of professional workers, we are actually incorporating the quadratic effect and the cubic effect. Okay, now here, of course, we actually incorporate more. Okay, I just wanted to take note of that. Okay, so because of that, in statistical analysis, what I'm gonna say, we cannot trust your R squared and the RSS when we have a model complexity. Okay, you can't really trust them. If you actually base your policy formulation on that, you're actually gonna mislead. Okay, and you know what? We don't want to mislead, and that is the reason why we need to be statistically guided. Okay, now I think I just told you now why we cannot actually trust uh, our R squared and our RSS when it comes to model complexity. Okay, then what can we now trust? What can we now use instead of them? Okay, anywhere in the world, what we use in a situation of model complexity is actually number one, adjusted R squared. It means uh, the conventional R squared need to be adjusted, okay? And the criteria number two is what we call the Akaike information criterion. And the criterion number three is what we call the Bayesian information criterion. But let me tell you this, if you take a look at the criterion number one, criterion number two, and criterion number three, we all try, each of them, we're trying to actually modify the residual sum square. You're going to see that now. Okay, so what I'm trying to tell you now, I present to you criteria in statistics that put into consideration the model fitness and model complexity. I'm going to say that again. I present to you now criteria that we use in statistical analysis, okay, that actually put into consideration model fitness and model complexity. Okay, if I want to talk about model fitness alone, I'm only going to talk about the residual sum of squared, which I call the RSS, and the R squared, which we call the coefficient of determination. But right now, I think the reason why we cannot consider, those criteria. Of course, I just told you, you cannot trust your R squared, you cannot trust your RSS or your situation of model complexity. And what we can trust is these three criteria. Okay, now what I'm trying to show you now is a formula for adjusted R squared. If you take a look at this formula now, you're basically you're gonna see RSS. Look at that. Okay, now I'm gonna see RSS, and this is our SST is the sum of square total that we call total variation, and of course the N is the sample size, and K is the number of regressors. So take a look at this guy now. This is the formula, for adjusted R squared. But let me tell you this: when you run regression in R, the adjusted R squared is actually going to be part of the output. Okay, so I just want to assure you that adjusted R squared is also going to be part of the output. I think I have a question here. As you increase your K, okay, the K is actually the number of regressors that we talked about the other time. When I increase K now, what is going to happen to the sum of square total? When I increase K, what is going to happen to N minus 1? When I increase K, what is going to happen to RSS? When I increase K, what is going to happen to N minus K? Now, let me tell you, I'm going to answer the first one now. When you talk about the SST is what we call the sum of square total. And you know what? The sum of square total actually we need is a variation around the response. I'm going to say that again. SST, which we call the sum of square total, is a variation around the response. So when you decide to increase the number of regressor, it doesn't really affect that. It doesn't really affect SST when you increase the numbers of regressor. And therefore, the answer to that is not changing. But what about N minus 1? The N minus 1 is just a number of, when you actually subtract 1 from the number of observation, okay, you are subtracting 1 from the number of observation. And you know what? When you decide to increase the numbers of regressor, I'm going to tell you, it doesn't really affect that. It doesn't affect that. The number of observation remain the same. The N minus 1 remain the same when you actually increase the number of regressor. Okay, so I just wanted to take note of that. But what about RSS? I think I said something the other time. When you increase the numbers, when you increase the regressor, the number of regressor, of course, I demonstrated to you the other time that the RSS is basically going to be going down. Okay, it's going to be going down. Okay, and what about N minus K? If you are increasing K, of course, N minus K is also going to be going down. Don't forget, you are subtracting what you are increasing from the sample size. I just wanted to take note of that. Now I'm going to go into the criterion number 2 now. Okay, the criterion number 2 is what we call the Akaike information criterion. And of course, we abbreviated that as AIC. Okay, we abbreviated that as AIC. And as you can see here, it's also a function of residual sum squared. I told you the other time, the 3 criteria are actually modify, adjust residual sum squared. Okay, so take a look at this guy now. Our N here is the number of observation and our K is basically the numbers of regressor. Okay, now when you increase K now, okay, what will happen to the residual sum of squared? Okay, and when you increase K, what will happen to 2 multiplied by K? So you can actually decide on that. But there's something I'm going to tell you. If we have our different competing modules, I'm going to say that again. If you have different regression modules that are actually competing, okay, if you really want to know which of that you're basically going to trust, you're going to choose the one that have the lowest AIC. I'm going to say that again. Using the second criterion, if you have different kind of modules and you have information about their respective AIC, you're basically going to choose the one with the lowest AIC. Okay, you're going to choose. Excuse me. Give me 1 second. Give me 1 second. Okay, I need to confirm if everyone is still hearing me clearly. Is everyone still hearing me? Okay, thank you so much. Thank you for confirming that. Okay, so like I said, using the first criterion, we're basically going to choose the model with the highest adjusted R squared. But using the second criterion now, we're going to choose the model with the lowest AIC. And I'm actually going to walk you through how you can actually run this in out. If you want to have the access to your AIC, okay, I'm going to show you how to do that in out. Okay, now I want to go to the third criterion now that we call Bayesian information criterion. Now, if you compare the Bayesian information criterion with the AIC, with the Akaike information criterion, you're basically going to see that here, they have the same. If you take a look at that here, they got the same, right? But when you take a look at the other side, this is 2 multiplied by K. But right here, it is a log n multiplied by K. The log n now is actually replacing 2. That is the difference between the AIC and the BIC. But let me tell you this. The rule of the thumb is that we're also going to select the module with the lowest BIC. Okay, so we're going to select module with the highest adjusted R squared. We're going to select module with the lowest AIC, and we're going to select module with the lowest BIC. Okay, I just wanted to know that. And you know what? Right now, I actually want to walk you through an example and the R code. And of course, I'm going to walk you through that now. Okay, now take a look at this now. We have 4 different competing modules. Take a look at this. If you look at the first module here, the numbers of regressors is 2. And if you look at the module here, we got 3 regressors. Here we got 4 regressors. Where we got 5 regressors. And you know what? Don't forget what we are trying to fit. We're trying to investigate the effect of the years of experience for professional workers on their salary. And we got 4 competing module. The first one is a module with 2 regressors. The second one is a module with 3 regressors. The third one is a module with 4 regressors. And the fourth one is a module with 5 regressors. And I told you the other time, if you want to compare these modules, you cannot use RSS. You cannot use R squared. So why is it that you cannot use RSS? Why is it that you cannot use R squared? Because they are not reliable when it comes to module complexity. And that is really what we're going to use. It's basically going to be AIC, the BIC, and the adjusted out squared. Okay, now if you take a look at each of the module now, we've already computed the AIC, we computed the BIC, we computed the adjusted out squared, and of course, I'm going to walk you through this in how you can actually compute the AIC and the BIC and the adjusted out squared of computing modules. Okay, but there's something I wanted to say here. Okay, when you want to compare now, you can compare all the module with the AIC, you can compare all the module with the BIC, you can compare all the module with the adjusted out squared, but there's something I'm going to tell you. There's possibility of a conflict of interest. I'm going to say that again. There can be possibility of the conflict of interest. Okay, we're actually going to choose the model with the lowest AIC. We're going to choose the model with the lowest BIC, and we're going to choose the model with the highest adjusted out squared. If you take a look at what I have now, okay, if I want to use the AIC now, I'm basically going to say the best model is this guy here, because the 299.2 is the lowest of all. Okay, if I want to go by BIC now, okay, if I want to go by the BIC now, I'm also going to choose the model here, because the lowest BIC is actually 308.1. But if I want to go by the adjusted out squared, okay, if I want to go by the adjusted out squared, I'm actually going to choose the model with the highest adjusted out squared. And if you take a look at that here, what you're basically going to choose is going to be this guy here. Take a look at that, this guy here, because it's 0.9241 is the highest. But let me tell you this, you're actually going to see that from the difference between this guy here and this guy here and this guy here, there's no significant difference between them. If you want to look at that very well, even if you actually take that to 2 decimal, if you take that to 2 decimal, you're basically going to have 0.92 for each of that. Okay, and therefore, based on that 2 decimal now, okay, I'm actually going to conclude that this guy is fantastic. I don't need to waste all weapon in my arsenal. I don't need to waste my regressors, because it's looking as if this is looking promising, because even if you continue to increase the numbers of regressor now, it's basically going to be around 0.92. Okay, so and that was why I said often this criteria identify a different model as the best. I just show you one now. Okay, but most of the time you're actually gonna see the AIC and the BIC, they basically gonna agree. And of course, if you take a look at the adjusted out squared, you're basically gonna see that the adjusted out squared that correspond to the lowest AIC and the BIC may not is the one that we're actually going to rely on at the end of the day. I'm going to say this again. The adjusted R squared that actually correspond to the lowest AIC and the lowest BIC is the one that we're actually going to choose. And in this case now, we're going to go for 0.9236, which is actually the one that corresponds to the lowest AIC and the lowest BIC. And that module now is actually quadratic regression module. What I'm trying to tell the world now, if you really want to look at the effect of the years of experience on the profession, on the salary of professional workers, of course, the best model you can actually fit for that is quadratic regression model, which is a polynomial of degree 2, which is a model, with only 3 regressors. Okay, now I think I've walked you through now. the criteria for module selection, the criteria that put into consideration, module fitness and module complexity. Okay, now we actually want to consider selection method now. Okay, what I just showed you is just a criteria. It is not a selection method. Okay, we use criteria in selection method, and I want to introduce you now to selection method in statistical analysis. When you have a good numbers of competing modules, of course, I'm going to say that again. In statistical analysis, when you have a good number of regression modules that are actually competing, of course, we have two ways to select. Is that we make use of subset selection, or we make use of a stepwise selection. Okay, now I'm going to start now using I'm going to explain what we mean by subset selection. Okay, this is a situation if you are trying to fit, if you are considering having the numbers of regressor to be 4 in your module. If you're not the number of regressor equal to 4, you're basically going to have the number of predictor variable to be 3. Look at that, x1, x2, x3. Okay, now the most simplest form of the model is going to be the one with the intercept. Now, this is the situation. For instance, if I got 3 variables, independent variables, okay, and I want to consider all different kind of modules, okay, that are within that framework. I don't know whether you remember in mathematics something that we call the power of a set. Okay, the power of a set. If I really want to know the possible number of subsets in a set, and basically, if I have a set A, okay, the possible power, number of subset is basically going to be 2 raised to power cardinality of a set. Okay, I tell you know that in mathematics, I'm going to say that again. You have a set A, okay, you got a set A, and the set A actually have maybe, for instance, it has 1, 2, maybe it has 3 elements. Okay, of course, if I want to figure out what is a cardinality, what is the cardinality of a set? Yeah, the cardinality is actually the number of elements you have in a set. And of course, if I have the cardinality, I can actually figure out the power of a set. And you know what? The power of a set in that situation is going to be 2 raised to power 3, and that is going to be 8. Okay, now we want to apply that to this now. Okay, you are actually you have 3 independent variables, x1, x2, x3, and of course, you now want to consider what we call subset selection, and you will now want to see how many modules that are within that framework. Okay, you're actually going to apply the idea of power of a set here. Okay, so it's going to be 2 raised to power the number of independent variables. How many independent variables do you have? You got 3, right? And it means we're actually going to have 8 modules. Now, what are the 8 modules? So this is going to be number 1. This is going to be number 2. This is going to be number 3. This is going to be number 4. This is going to be number 5. This is going to be number 6. This is going to be number 7. And this is going to be number 8. Okay, so take a look at that. We are actually applying the knowledge of the power of a set in mathematics. Okay, so is there anyone want to ask question about that before I move on? If you really understand that, if you get that now, I need you to say yes or you comment yes, what I just said now. If you understand how I got 8 modules, Okay, I need you to say yes or you comment yes. And if you don't understand, I need you to ask question now. I'm going to re-explain if you ask question now, if you don't really understand. Okay, so which means you basically understand what I just explained, right? Okay, now these are the, so with this now, we're basically going to have uh 8 possible models. If you look at the first one here, it's going to be intercept. I remember in mathematics, uh, when you're talking about the power of a set, okay, part of the element of the power of a set is basically going to be empty set. Okay, y on 1 now is more or less like you are actually, you are actually having an empty set. It's like you are considering situation where you do not have any predator at all. Now, when you now want to go to a situation where you have one predator, since you have 3 predator here, it could be Y on X1, it could be Y on X2, it could be Y on X3. Okay, so these are possibility. Now, if I want to look at it, if I want to have it, a pair, a possible pair, okay, or of that, instead I have S1 with S2, I can have S1 with S3, I can have S2 with S3. So take a look at that. And this is the last one. Okay. Now, when you take a look at all of that, now you're basically going to see that this guy here is the simplest form of the model. Okay. And this guy here is a complicated one. Okay. So take a look at that now. Okay, so in general, when we have k terms in the full model, okay, they want to ask you the k term in the full model. Okay, so how many potential model do we need to consider to find the best model? Okay, now the k term actually means, here when you have k equal to 4, for instance, okay, here we are actually using k. K is the number of regressors when you take a look at this guy now, okay, k equal to 4, right? But p equal to 3. So p is a number of independent variables. Okay, I just wanted to see the difference between k and p. I'm going to say that again. K represents the number of regressors. Y or p represent the number of predators or the number of independent variables. So if I want to figure that out based on k now, it's going to be 2 raised to the power k, okay, minus 1. Okay, 2 raised to the power k minus 1. But if I want to do that in terms of predator, it's going to be 2 raised to the power p. Okay, don't forget, okay, p, okay, is equal to k minus 1. I just wanted to take note of that. The number of predator is actually equal to the number of regressors minus 1. So situation where you are actually giving the number of predator or the number of regressors, using that formula now, you can actually, tell what the number of possible models is basically going to be. Okay, so far so good. I want to talk about something now really quick, something that we call strengths and weakness. Okay, when you take a look at the up-subset selection approach, the up-subset selection approach, of course, the strength of that approach is because we actually, before we decide on the best regression model, we're going to go through all the possible regression model. Take a look at that now. Okay, so that is the strength of the all subset selection. We're actually going to walk through all the, possible model within the scope. But what is the weakness? Okay, what is a weakness? The weakness is a computation. It's going to be computationally expensive when k is large. Consider, situation where you have like 15 independent variables. Okay, if you have 15 independent variables, that means the numbers of regressors is going to be 16. Okay, imagine 2 raised to power 16. That is going to be a lot of modules that we're basically going to walk through. Okay, so that is a weakness of up subset module. Okay, the weakness of up subset module, or up subset selection is it becomes problematic. The computing that is going to be problematic when the number of regressor is very large. Okay, that is exactly what I'm trying to talk about now. Okay, now the other time I said we got 2 different kind of selection. The simple right now. So thank you so much. Okay, today I'm actually, like I said, I'm gonna be walking you through